This graph plots a software system's failure rate over time. When hardware wears out, physical parts degrade, but software doesn't rust. It degrades precisely because we change it. When a developer patches a bug or adds a feature, they introduce a sudden spike in the failure rate. Over the months and years, these updates accumulate. Every modification carries a risk of unintended side effects, creating more errors down the line. Gradually, the minimum baseline failure rate rises, and the overall health of the software deteriorates. This entire cycle usually begins with a simple user request for a new capability. To fulfill that request safely, an engineering team cannot just open up the source files and start typing. Instead, the request must pass through a strict sequence known as the change control workflow. A change request is submitted, evaluated for impact, executed by the engineering team, and finally deployed back to the users. Without enforcing this standard sequence, independent changes collide, documentation falls behind, and the internal architecture of the program rapidly collapses. The evaluation stage is governed by a Change Control Authority, or CCA, weighing business value against technical risks. Once cleared, developers access the project repository, checking out specific, isolated code-based components, known as software configuration items, or SCIs. Often, developers open an SCI to find a tangled mess of undocumented, heavily patched spaghetti code. When the code is this chaotic, the time required to analyze, implement, and test a single update skyrockets. The mean time to change metric becomes unacceptably high. At this threshold, normal patching routines fail. To make the code maintainable again, the team must abandon minor fixes and initiate a comprehensive overhaul. This overhaul follows the software re-engineering process model, a cyclical framework designed to revive degraded legacy systems. Bypassing initial inventory analysis, the team begins reverse engineering. They scan the messy source code to extract the underlying logic, generating clean, abstract structural models. With the old logic exposed, the team moves into code and data restructuring, stripping out outdated practices and mapping the architecture to modern design standards. Next comes forward engineering, using those cleaned, abstract models as blueprints to generate pristine, executable source code. Let's test this logic. If your objective is to migrate an outdated flat file data structure to a modern relational database, which two specific steps of this cycle must you perform? You need reverse engineering to untangle and map the existing legacy data relationships, followed by data restructuring to design the new relational database architecture. Reverse engineering looks backward to understand the past, while forward engineering physically builds the future system. Before this newly built code ever reaches the user, it undergoes rigorous software quality assurance testing to verify that it functions exactly as intended. Once the re-engineered SCIs pass testing, the execution phase ends, and the finalized components must be routed back into the main system repository. Checking these optimized items in establishes a new, stable system baseline. The baseline locks the code into an official, deployable release. Here is your master view of the process. Pause the video and capture this workflow. Maintenance relies on the strict linear checkpoints of change control, while deep system decay is countered by the cyclical re-engineering model nested within it. Enforcing a bureaucratic sequence manages the daily demands of users, while structural overhauls rebuild the underlying foundation. Operating both mechanisms correctly guarantees that legacy systems will remain viable for years to come.